Hello students, uh, how are you? Hope you are fine, doing well. Okay, so let me introduce myself first. Myself Wasiya Karanjum. I have done M.Pharm in pharmacology from Jamia Hamdard. So after that I joined Jamia Islamia and worked there as a guest faculty. And I also worked there as a senior research fellow. My research topic there was heart failure. And then I switched over to Wipro, where I worked as a pharmacovigilance officer. Then to Saudi Arabia I moved. There I worked as assistant professor of pharmacology and taught PharmD students their pharmacology. For last 8 years I have been working as the NEET bio faculty, and currently also as the NEET bio faculty I am working in the Hind Guru Academy. I hope and strive for your bright future in medical profession. And let us start first today with an electrocardiophysiology topic, that is ventricular action potential. So this ventricular action potential is something related with ventricle. It's a part of heart. It's actually the pumping part of the heart. So pumping part of the heart means the heart is meant for pumping actually. So pumping is meant for the transport of many of the molecules like nitrogenous waste, like nutrients, like oxygen or carbon dioxide to its destinations, to the body parts where it is either required for certain activities, physiology, or it is removed finally like nitrogenous wastes in kidney. So students, this ventricle we will study in the structure of heart, but what about action potential? So action potential is the electrical activity. It is generated from in the cells, in the cardiac cells, and initially the impulse is generated in the nodal muscle cells like SA node or AV node. Then it is transferred to the cardiomyocytes lastly, where the action potential generates, which we will study today. How? With the exchange of ions, and those exchange of ions or flow of currents will be measured in terms of millivolts against the time scale, and that will be called ventricular action potential. So first we will take a look of the heart. This is the schematic diagram of heart, starting with these two atrium, one in the left side and one in the right side. So it is left atrium, it is right atrium. Likewise it is left ventricle and right ventricle. So this is the main pumping organ of the heart, that is left and right ventricle. So left ventricle is stronger and pumps blood to the body parts, while the right ventricle pumps to the lungs and it is relatively less strong. And these are the left and right atria, which are the receiving ends. So here at the right top corner there is an SA node, sinoatrial node, which is a nodal musculature which generates electricity. So those electrical activity in ECG will be recorded at the skin level, but when we will study about the ventricular action potential or a ventricular cell myocyte, then it will be recorded through the microelectrodes put inside the cell and measured in the form of membrane potentials or millivolts. So first we study about this SA node and this AV node, atrioventricular node. So these nodes are the nodal musculatures giving currents to atrium as well as this AV node, and AV node starts with the bundle of his bifurcating into left and right bundle and finally culminating into the Purkinje fibers. Purkinje fibers gives the electrical activity to cardiomyocytes generally in the heart system, but in the isolated system we will put some impulses. So we will put some pulses of electricity, and compensating for this the activity generated from the SO node originally. So there we will suffice with the electrical pulses from outside, and action potential will be generated as normally it is generated in the case of cardiac activity. So this cardiomyocytes isolated will look like this. Here in between the cells there will be intercalated discs with the separating cells. So from one cell the action potential will travel to the next cell through these intercalated discs. Intercalated discs. So this transfers the action potential, and this way a coordinated activity of the whole heart takes place in the case of heart, which is absent in the case of skeletal muscles, where intercalated discs are not present. So with this introduction, sufficient introduction, I start just with the ventricular action potential. So ventricular action potential begins with the resting potential and a peak of depolarization, then a faster or initial repolarization, then a plateau, and again a rapid repolarization, achieving the resting potential again. So this same activity, it starts at the minus 90 millivolt and peak is achieved at plus 50 millivolt. So here it is millivolt and it is a time scale on the x-axis. Normally on the x-axis a constant term like time is recorded. So the resting potential is a polarized state where the ions are polarized and takes a negative inside and positive outside form. So it is polarized form. So this polarized form is not due to the negative or positive ions polarized, but the relative proportion of positive ions lesser inside makes it negative and makes it more positive outside because of the relatively more positive outside. And those positive ions are sodium and potassium ions. An extra positive ions, calcium, is also present in heart, which is absent in the skeletal, which is absent in the case of neuronal action potential. So there this stage will not be there, which is due to the calcium ions. And you know this calcium channel ions are tolerated for many of the cardiac drugs like calcium channel blockers. So this polarized state will be reversed that means the negative outside and positive inside, and this will be depolarization or rapid and transient sodium entry. So this will make it depolarized or reversal of the polarized state. Depolarization is reversal of the polarized state. This spike is depolarization. Then this stage is an initial repolarization. And this is due to the potassium exit, and the sodium entry is blocked and there is a potassium exit. So this potassium exit will cause an initial fast repolarization, and then it is balanced through the calcium entry. So this calcium entry will balance this potassium exit and make it a plateau or sustained repolarization. And lastly, there will be a rapid repolarization due to again a potassium exit like it was there in the initial repolarization. So this potassium exit again will make it further down and rapid repolarization. Repolarization. And this will achieve the resting potential that will be maintained through the potassium permeability. Increased potassium permeability. When this repolarization, when this potassium exit is delayed, then it will further go down. This potential will further go down below the minus 90 millivolt level, and that will be hyperpolarization. So hyperpolarization is an inhibitory stage. Inhibitory stage. So you know, if the action potential is generated, there will be a contraction, systole. But when there is a hyperpolarization, the achievement of next action potential will be stopped until the resting potential again is achieved. That will take time, and until that an inhibitory stage will be there, that is hyperpolarization stage. So this is all about the ventricular action potential. So you know, as I have told, this calcium level is not present in the nervous tissue, so in that this sustained stage will not be there. Otherwise all the things will be there, but the maintenance of this resting potential will be through sodium potassium channel. So sodium potassium channel there will maintain this resting potential, but here it is through the increased potassium permeability. So you must be knowing that what are the implications of this ventricular potential, action potential. So how we can use this knowledge? So this knowledge will be used this will contribute to the ECG, where we can diagnose many of the heart diseases. Of course, many not, like the damage of the part of the heart. So many of the diseases which will be diagnosed through ECG, where the contributory part is this ventricular action potential. All these stages like repolarization, depolarization will there also be in the ECG. So there we can achieve to diagnose the hypokalemia or hyperkalemia or cardiac arrest or bradycardia, tachycardia. Many of the heart diseases like arrhythmia can be diagnosed by the changes in the normal ECG. Hope students you have understood the things. If you have some query, you can ask. Don't hesitate. You can ask any of the relevant doubts. Okay. Thank you for watching.